Wonderful. I think we are live. So welcome everyone to this Astronomy on Tap Urbana-Champaign. And today we will have Alexander Deich. I can never pronounce his last name. And I think that's why he hates me. So he's not at the moment here in Urbana-Champaign. And he just confessed that it's because I'm too annoying. So hopefully he will come back when things get better. So Alex is a graduate student in the physics department at the University of Illinois in Urbana-Champaign. He graduated from the Reed College in 2016 and then moved to Oregon State University, where he worked on modeling the emission from off-axis gamma ray bursts. And then he also worked for the Swift Space Telescope, where he focused on automatic emission planning software. He is interested in many things, but in particular in novel observations of testing general relativity with multi-messenger astronomy, numerical modeling of complex astrophysical phenomena. But it's also interesting that Alex, he also likes to use mathematical and computational techniques to study things like modeling the nerve response in mice and things like that. So, and I think today's talk will be related to the other thing that Alex likes a lot. So remember that you can ask questions over the YouTube chat and perhaps over social media, Facebook or Twitter, or you can email our Astronomy on Tap section. And then the questions will be read at the end of the talk, or maybe if you want, I can also interrupt Alex for the question. Now, without further ado, we will turn time to Alex.
Thanks, Alejandro. Hey, thanks for coming to the talk, everyone. I'm Alex. And so, yeah, so as Alejandro said, this talk isn't so much exactly on what I do every day for research. It's more, because what I do has to do more with gravity and stuff. And I know that there have been a lot of Astronomy on Tap talks about gravity recently. So I'm branching out a little bit, and hopefully I don't get things too wrong for not being totally up to date on it. But I certainly find this topic really interesting, and I find this story really compelling. And the story that I want to talk about comes from an observation about how we interact with the universe when we're learning about the universe, and in particular, when we're doing science, or indeed if we're just looking at a picture like this of the Andromeda Galaxy, there's this sort of there's this sense that we're sort of removed from what's going on. Like, I certainly have a feeling like I'm an audience member watching a play unfold before me, and like doing science means learning like the rules of the play and guessing where it's going to go next. But I always feel a sort of distance with that. But ultimately, we are made out of the same stuff as the rest of the universe is made out of. And so in studying the universe, we ultimately learn a lot about ourselves, our own place in the universe, and we have a much greater sense of belonging, I feel, after learning about this sort of thing. And so that's sort of what informed how I broke this talk up into two parts. The first part, I'm going to go over what we're made out of and where they came from. And then in the second part, I'm going to zoom in a little bit and talk about one very particular water molecule in you and trace its path over cosmic history. So to start with part one, your atoms and their history in the universe. To start this, I want to just look very broadly. Just what is this? What are you made of? What are your stats? Just in a few bullet points. First of all, you're made of a lot of atoms, like an incredible amount. In 7 times 10 to the 27 atoms. Now, this is a huge number. I don't need to tell you that, but I don't really have intuitive understanding of what that number means. And so, and like 10 to the 10 is a huge number. And apparently this number is way bigger than that. So to get a grasp of what that is, the best comparison I can come up with is that this number is much bigger than the number of grains of sand in the world. And so it's many orders of magnitude bigger, in fact. And so that just, I like to start there just because it reminds us that we are really complex organizations of building blocks. And then if you were to take a broad scale view of what most of those atoms are, you would find that by weight, almost all of them are carbon, oxygen, hydrogen. And this is pretty interesting, I think, because this doesn't, while it's true that we're mostly carbon, oxygen, and hydrogen, it's obvious that if you were to just take those three things, you wouldn't get anywhere close to a human. So clearly, like, the interesting stuff of being a human and the things that you need to make being a human work require a lot more than just that. And it requires a lot of stuff that we have very small amounts of. And then finally, these carbon, these oxygens, and these hydrogens were made in the universe. Some of them were made very early at the Big Bang, and others were made much later on in stars. But the average age of an atom in your body is about 7 billion years. And that always kind of blows me away, because I'm 20 something years old. But when I say that I'm 20 something years old, what I really mean is that the process of consciousness has been going on for me for that amount of time. But the things that are doing the process of consciousness, the structure and the pattern of consciousness, those things themselves are ancient, and they're ancient products of the universe. And when we look out across space, we see the same building blocks everywhere. So to get more specific about what exactly we're made of, here's a chart that breaks things down a little bit more clearly. So as I said before, we're mostly carbon, hydrogen, and oxygen. And then these are the most common elements in our bodies. We don't have any helium, but I included that in the chart because I want to make a comparison later. But yeah, so what's interesting is that we know that we have a lot of iron, and we have calcium in our bones and all that, and our brain needs a lot of potassium to make the synapses work. But those all constitute very, very small pieces of who we are. But meanwhile, what's kind of nice about this chart that I think is kind of funny is that, like, when you learn about humans in like elementary school, you learn that we are like mostly water by mass, right? Like we're like 70% water. And then also that we're carbon-based life. Like, those are the two things that you learn about being a person in like elementary school. And sure enough, in this chart, you see that, okay, yeah, the hydrogen and the oxygen, those combine to form water. And then it's surrounded by a sac that's made out of carbon. So, you know, we're watery carbon sacs, which to first approximation is basically what a person is. But if we're interested in like where these things came from, we might want to ask about how does this breakdown compare to our surroundings, right? Like, it might just be the case that this is just what stuff is made of around us. And so, and if that's the case, maybe we're sort of, it's natural that we're made of this stuff. But when we look at the crust of the Earth, which is where we've evolved and like spent our entire geological history, we find that the crust of the Earth is actually much different. The crust of the Earth also has a lot of oxygen in it, but almost all of the stuff that's in the that makes up the mass of the Earth, of the crust of the Earth, is things that we have either very small amounts of or none of in our own bodies. And that's kind of interesting. And so then you might ask, okay, but we also live in a solar system, and almost all of the mass of the solar system is in the sun. So how does our own composition compare to that of the sun? Maybe that's very similar. And it turns out, again, it isn't. The sun is almost entirely hydrogen and helium. And so I find this chart really fascinating because these are three organizations of atoms, our bodies, the Earth, and the sun. but and we all came from the same sort of region in outer space, but there are clearly a lot of differences in how we're constructed, and so that sort of suggests that there might be really interesting processes that dictate how the different elements get distributed between us. So to talk about how the about where those elements come from, I'm going to break down each of these elements that I have on the screen, and I'm going to start with the lightest ones first, and then go down as they get heavier. And I'm going to start with the lightest ones because in order to make an atom, you want to smash some protons and some neutrons together, right? The atoms are made of protons and neutrons. And the bigger the atom gets, the more energy you need to smash them together. And so it might make sense that the most numerous and earliest atoms to be created are the lightest ones, the ones with the simplest structure. So we'll start there. Now, the lightest elements in the periodic table, which are hydrogen and helium, were created at the very early universe, so about 3.8 billion years ago, just minutes after the Big Bang, in fact. So back then, the universe was incredibly dense and hot. The temperatures were in excess of 1 billion Kelvin. And at that temperature, you have lots and lots and lots of little protons and neutrons zooming around and occasionally bumping into each other. And the temperature is so high that each of these protons and neutrons, it has an incredibly high velocity. And so occasionally, a proton and a neutron will race towards each other and slam into each other. And when one proton and one neutron slam together, you get one type of hydrogen. So hydrogen is any element that has a single proton. And then the number of neutrons it has determines what isotope it is. In this case, if it has one neutron, it'll be an isotope called deuterium. And when the two subatomic particles collide, they release a lot of energy when they fuse together, creating the new atom, and that energy is given off in the form of light, and that'll be important later. However, as this was happening in the early universe, about 13.8 billion years ago, the universe was also expanding very, very, very rapidly. And so it wasn't very long before the universe had expanded and cooled down sufficiently to the point where not only were the subatomic particles going much, much slower, but the odds that any two would impact each other were much, much lower. And so it wasn't long before this sort of thermally caused fusion wouldn't work anymore. And so for that, we need a much different mechanism. So the thermal energy isn't useful anymore. So we need another mechanism to speed up subatomic particles in order to smash them together to make atoms. And one useful thing that was happening at this time is that the universe wasn't homogeneous. There were clumps here and there where there was slightly more hydrogen and slightly more helium. And in these regions, there would be slightly more gravity because gravity is proportional to how much mass there is. And this gravity would pull other bits and pieces, other hydrogens and other heliums towards it. And as they, and as you can tell, this would pretty quickly become a self-fueling process. So the cloud would gather more protons, which would make it heavier, which would give it more gravity, which would attract even more. And as this was happening, the protons that it's attracting and the neutrons and the hydrogens and the heliums are going faster and faster and faster because the gravity is getting more and more and more. And as the gravity increases, there comes a point where the hydrogens and the heliums are accelerated so much that they can actually start to fuse at the center of the gas cloud. And this creates a star. So a star is effectively just a gigantic gas cloud that is constantly fusing smaller elements together to create larger ones. And the way that a star survives is that it's really a balance between two different forces. One is a gravity that's pulling everything towards the center. And the other, as I talked about earlier, when you collide two atoms together, they will release a lot of energy in the form of light. And so that provides the other force that pushes against gravity. And so radiation pressure is pushing everything out. And so at the center of this star, you're creating a lot of new, heavier elements that didn't exist at the time of the Big Bang. And so in this way, it's common to think of stars as factories for new elements. And this state of being a balance between gravity and pressure pushing outward is called hydrostatic equilibrium. And stars exist in hydrostatic equilibrium like our sun until they run out of fuel. At that point, the interior of the star can no longer sustain the pressure due to the gravity, and the star shrinks a little bit. But the shrinking will heat everything up, and it will reignite fusion in outer layers of the star, so it'll actually grow a little bit. But they can't sustain this forever. There comes a point where it has to stop fusing. And at that point, the star will collapse and eventually explode. And exactly what kind of explosion it undergoes depends exactly on how heavy it is. And that's what I'll talk about next. So yeah, if there are no questions, I'll continue. So for a lot of the lighter elements that are heavier than helium, or lithium rather, I should say, these atoms are formed in stars that are similar in mass to the sun. So the sun isn't the lowest mass star, but it's by a long shot not the heaviest. And so for the sun, nothing really above oxygen gets produced, and eventually, so this is the process I was talking about earlier, where the star expands and then collapses and explodes, and the point here is that when the star is sort of at this phase over here, where the when the star is a sort of inflated big red ball that is near the end of its life, it's filled with very, very rich material, lots and lots of metals and things that didn't exist beforehand. And so the explosion is necessary in order to seed the rest of the universe with that material. And that's exactly what happens when the star sheds its outer layers as it's exploding. It's giving the rest of the material to the nearby galaxy, and what's left behind is an object called a white dwarf, which is almost entirely carbon, nitrogen, and oxygen usually, but there are other types with other elements in them, and they aren't fusing anymore. They aren't heavy enough to fuse. They're about as big as the Earth, and they are incredibly hot, and they stay hot for a very, very long time, like tens of billions of years. In fact, it's thought that there doesn't exist a white dwarf that has cooled down yet, because the universe hasn't existed long enough to let one cool down, which is kind of interesting. But so that is very often the end of the story for a white dwarf, but it doesn't have to be. If a white dwarf is in a binary orbit with another star, and so a binary orbit just means that there are two stars that are orbiting each other, orbiting around like that. If a white dwarf is in such an orbit, then it can be pulling material off of its companion star like this. And as it does so, it's collecting more and more mass onto itself. And that can kickstart another chain reaction that can explode the white dwarf again and cast out even more material into the surrounding galactic neighborhood. And just for scale, here's a picture of the Earth. So white dwarfs are really tiny, but like on the scale of a star, but they're incredibly dense. So when this happens and a white dwarf explodes, that seeds the nearby galaxy with everything that you need to make people almost. It's up through oxygen, and the explosion of the white dwarf takes you all the way through zinc, basically. And this is called a type 1a supernova. And they're incredibly bright events. And when they happen, they overpower in luminosity all of the other stars in the galaxy. And these have been observable from Earth a couple of times in human history, and the written records report that you could read a book by the light of this exploding star at night. So here's a little animation of that happening. So you can see the white dwarf accreting material off of its companion until it gets so big and it just blows up, ejecting its enriched guts into the cosmos. Now, so that takes us up through zinc, but we need a lot more. We need more energy in order to make much bigger elements, and so for that we need an even bigger star. And how big can stars get? Well, really big. So this is a great illustration that shows the scale of stars in our galaxy. So in the middle, there's a single pixel that represents the sun. And then surrounding it are a bunch of illustrations of stars drawn to scale. And as you can see, there are stars that are to the sun what the sun is to the Earth. It's really it's incomprehensible. It's sort of like when I talked about the number of atoms in the body. Like our brains just aren't really designed to understand this in any meaningful way. But what happens with a much bigger star like this is that they are able to fuse up to iron very, very quickly. And after iron, the fusion of new elements stops giving them more energy than they're putting into it. So an active star won't really make elements up past iron, although exceptions do exist. But what'll start happening is the outer layers of the star will start burning sequentially lighter and lighter elements. And so you get this sort of onion structure to the star, where each layer of the onion is a different element that's being burned into the and fused into a heavier and heavier one. And so when these stars run out of fuel to burn, they don't leave any remnant like a white dwarf. They will either become a black hole, or they'll leave an even denser object called a neutron star, which are extremely fascinating and would make for a good AOT, but that we don't have time to get into today. But when these things explode, you get what's called a type 2 supernova, and they leave behind these incredibly beautiful nebulae, like this, which is the Crab Nebula. And it's thought that a couple of these were what seeded a star system like our own. So let's review really quickly, because that was a lot of information at once. So there are a couple of ways to form atoms in the universe, and depending on how massive the atoms are, they will have taken a different route. Sometimes, for the lightest atoms, they're almost entirely formed just at the Big Bang. Other atoms were formed by small dying stars, like the size of our sun. Other atoms were formed by explosions of huge stars, like the onion star that I just showed you. And notice that the colors in this periodic table that I'm showing you are much more complicated than the story that I was just telling you. It by no means is the case that if you know the mass of an element, do you know exactly where it came from? Because different methods can produce the same elements for sure. And then some of these are explosions of small stars, like the white dwarfs that I was talking about. And then two of these are commonly formed by cosmic rays, which was not really a thing that I mentioned, because the two elements that these are responsible for aren't super important for life. But a cosmic ray is an incredibly high energy photon that comes from deep space. And when that hits certain atoms, it can actually break them apart into either beryllium or boron. And then finally, every single other atom that's listed on this periodic table is created in a neutron star collision, which is pretty fascinating, because that means that all of the atoms that we need in order for life to exist on Earth as we know it, all of these atoms, with the exception of hydrogen and helium, required a star to explode. And I'm always just like really blown away when I think about that. Another thing that I'll mention is that I've blocked out a lot of the elements in this periodic table, because those are elements that are not found in nature, usually because they're so radioactive that they will decay very quickly into other more stable atoms. And so the only places we've seen them is in the lab when we create them explicitly. So that is part one. You are composed of elements, some of which are left over from the Big Bang, and others of which were formed inside of dying stars. And your existence is contingent on stars exploding. Your existence and the existence of the Earth is contingent on stars exploding. And that's, whenever I think about that, that always I always feel a kind of fuzzy connection. I think to the rest of the universe. It's truly profound. So now we can zoom in a little bit and follow the path of a single water molecule. A water molecule like what many of you, I'm sure, are drinking right now. So part two, the adventure of a water molecule in you, how you came to possess it, and where it'll end up. So the setting is that several the solar system is starting to form. Several supernovae have gone off, and they've seeded a region of the galaxy with a rich cloud of dust. This dust is mostly hydrogen, but it has some of the heavier elements that we're used to. And the cloud slowly coalesces. And the interior of the cloud gets very, very, very hot. And in exactly the same way that I was just describing earlier, the interior of the cloud is going to attract more and more stuff until it ignites into a star. The hydrogen starts fusing, and the sun is born. And then in orbit around this new star are a bunch of small clumps of dust that first begin to turn into pebbles, and then into boulders, and then into planets. And these are slowly becoming the planets that we know today. As this is happening, the the soon-to-be planets are incredibly hot because they're constantly being bombarded with other rocks in the dust cloud. And so basically all of the planets are totally molten. What I'm showing here is a picture of just such a dust cloud from the Hubble Space Telescope. And above are the actual pictures where you can see hints of the dust cloud, and then below are artist impressions of what it of a more helpful picture of what it looks like. And an interesting technique that like a tool of the trade that this is exploiting is that if you were to just take a picture of the cloud with the star directly, basically nothing would be visible because all of the features of the scene would be overpowered by the light from the star. And so a common technique for imaging these sorts of things is to put a little dot on your detector or over your detector, exactly where the star is. And that blocks out all of the light that comes directly from the star. And so you're left with only the light that is reflected off of the nearby features that you're interested in. This is a technique that's commonly used when you're searching for planets that are outside of the solar system. And it's a cool little trick. So slowly but surely, the Earth starts to be formed. And as I said, it's incredibly hot because it's constantly being bombarded with other asteroids. And so water can't yet exist on the surface of the Earth. It would immediately evaporate and boil off, and the hydrogen and the oxygen would become unbound from each other because of all of the radiation. At the same time, the young solar system was incredibly messy and is filled with all of these boulders that are zooming and crashing into each other everywhere, spewing debris. However, a lot of these rocky bodies that are causing so much chaos are from further out in the solar system, where you can have a lot more water ice because they're further from the sun, so it's not as hot. And out there, the region is less dense, so you don't get as many impacts per day or whatever. And so it's thought that the currently accepted explanation is that the water that you're drinking right now probably came from one of those rocky bodies impacting the Earth. This was all about 4.5 billion years ago. And this process of creating the planet Earth and populating it with water took a few hundred million years. And it was sometime in those few hundred million years that the water that you're drinking probably arrived on Earth from one of these rocky bodies. Now, I should say that this story of water arriving on a comet or an asteroid is pretty contentious, and it's a topic of very active research. We're still not sure, and there are people who think that there was enough water on Earth to begin with, and it was sort of hidden on the interior. But the majority consensus at the moment is that it probably came from asteroids. So the Earth was experiencing at this time also a lot of volcanic activity because, as I said, the interior or the whole planet is totally molten, and the Earth is being it's going through a lot of sort of adolescent changes, where the interior of the planet is belching out because it has a lot of pressure all of a sudden from all of this new mass that's accumulated onto it, and at the same time it's getting bombarded from the outside by all these asteroids. And so as this is happening, a lot of gases are being spewed into the atmosphere around Earth by these volcanoes, gases like methane and carbon dioxide. And so these gases help insulate the Earth, and they help actually create a more stable atmosphere for where liquid water can start to form. And so at some point around 3 billion years ago, 3.5 billion years ago, this is what the Earth might have looked like, where as you can see, you have huge regions of still molten rock, but at the same time, you're forming oceans. And the water molecules that you're drinking right now and that are in your stomach right now were probably in these oceans about 3 billion years ago. Eventually, life was formed. And that's a very astrophysicist way of describing all of biology. But life evolved, and with it, the atmosphere changed into an oxygen-rich atmosphere instead of the carbon-rich atmosphere that it started out as. And that was largely propelled by eukaryotic life. And we have the Earth that we know today. And today, that water molecule that you're drinking is active in this big cycle called the water cycle, which is the process by which water is deposited on the ground or in oceans, and then goes up into the atmosphere and then comes back down as rain. And it's an incredibly complicated process, and we're still learning stuff about it all the time. But the point is that the water molecule that you're drinking right now it has a very sedentary life for most of the time. It's usually either in an ocean or underground. And groundwater can spend about 10,000 years beneath Earth's surface before leaving. And it can be even older than that in the case of some like really old tectonic plates. For instance, I think Iceland is incredibly old, and it has like 100,000-year-old water beneath it. And at the same time, the major ice sheets, like in the North and South Poles, are very, very long-term storage containers for water, where they can go almost a million years without going anywhere. And so the upshot of all of this is that it's relatively unlikely that you've actually drunk the same water molecule twice. And indeed, it's even it's also kind of unlikely that anyone else has drunk that water molecule, because when you're done with this drink, and at some point during either tonight or tomorrow, you will expel that water molecule either through perspiration in your sweat, or through evaporation out of your mouth, or through some other process that you'd have to go to Anatomy on Tap to learn about. Then after that, the water will almost immediately go into the atmosphere. It'll almost immediately evaporate. And it stays in the atmosphere for only about 9 days before coming back down as rain. But when it comes back down as rain, it very rarely goes into drinking sources for humans, because drinking sources for humans are almost entirely from groundwater, which is relatively old. And so if it doesn't go into the ground, it'll go into the ocean, where it stays for a very long time. But the point is that every water molecule that you interact with is a new water molecule, and it's one that probably hasn't even been in an animal before. This is in contrast to atmospheric molecules. So like an O2 molecule, so two oxygens bound together that you breathe. There are so many atmospheric molecules, and the atmosphere is incredibly homogeneous. So when I breathe out, my breath very quickly disperses into the atmosphere, and it mixes all together. That it's a relative certainty that every breath I take has been breathed in by someone before, and almost definitely someone very long ago. So it's a very common like homework problem in like a statistical mechanics course, for instance, to show that with every breath that you take, you're almost definitely breathing in molecules of air that Caesar breathed out in his last breath. And that's a function of the fact that there is no real sink for air molecules. When you breathe stuff out and breathe them back in, they're for the most part going to stay in the atmosphere. if they do get sucked into like a plant or something, it's not very long, only like, tens of years before that gas is released back into the atmosphere somehow. So that's what your water molecule is doing right now. And that's what your water molecule will be doing for about the next 500 million years or so. So the water cycle is going to persist for as long as the temperature and pressure on the Earth stay basically as we know them today. And that depends on what the sun is doing. However, in about 1 billion years, the sun is going to start running out of its hydrogen fuel. And as that happens, it's going to start expanding, like I described earlier. And as the sun expands, the Earth is going to heat up. And at that point, something really interesting will have happened, actually, is as part of the water cycle, I don't know if you noticed this, I'm going to go back briefly, but as part of the water cycle, one of the things that water can do is get subducted beneath the plates of the continental plates on the surface of the Earth. And by the time that the sun is expanding rapidly, almost all of the water on Earth, about 80% of it, will have been subducted underground, which is pretty interesting. But in about 1 billion years, most of the water on Earth will have been subducted under the surface, and then the really hot sun is going to start heating up the Earth in a runaway event. And at this time, it's thought that the surface of the Earth is going to look a lot like the surface of Venus, which this is a picture of. So in the 70s, the Soviets sent a bunch of probes to Venus, and it's kind of funny. I went looking for the pictures that the probes sent back, and they're not on Wikipedia, which is weird because Wikipedia has like every space picture. And so I had to go to the NASA website to find them, and it said that they weren't necessarily in the public domain because they're like the Soviet Union's pictures. So I don't know. I don't think it'll be a problem for this talk. But the point is that this process will evaporate the oceans, and if the water is underneath the crust, then the water that's in your stomach right now will be evaporated and sent into space. One really interesting thing. So as the sun expands, the region where the distance from the sun where life can exist will also grow, right? So right now, the distance from the sun where life can exist is somewhere near where Earth is. But in the future, when the sun expands, that distance will be pushed out. And by this point, where Earth looks like Venus, Mars will be in the habitable zone. The ice caps on Mars will actually melt in about 1 billion years. And it's thought that at that point, life could actually develop on Mars and live for a few 100 million years, which is pretty sweet. So eventually, the sun just keeps expanding, and the Earth is going to be turned into a barren landscape. And any water that was anywhere in the Earth, regardless of if it was under the crust or not, is going to have been evaporated and it escaped into space. And once it's in space, it's subject to a lot of solar radiation. And this solar radiation is going to split the hydrogen and the oxygen that's in the water into the constituent atoms. And then those atoms are just going to be in orbit of the sun for the next several 100 million years. At this point, it's unknown what will happen to the Earth. It will either get kicked out of the solar system. So the sun is going to go through a white dwarf phase where it keeps expanding and then collapses in on itself and explodes. And the Earth and the Moon might get kicked during that event, or they might fall into the sun as it loses mass. And we just don't know what will happen yet. It's interesting to note that because of chaos theory, it's actually impossible to predict what the position of the planets will be more than 250 million years from now. And so we really have very little idea of what will happen to the planets at this stage. But so the water that's in your stomach right now, it will have been split into oxygen and hydrogen, and then it will be wandering throughout the solar system. The sun will eventually blow up, and a white dwarf will be left behind. And in that explosion, it's very possible that the hydrogen and the oxygen will get kicked out and just be free floating through the universe. However, at that point, the universe is still expanding, and it's going to keep expanding as far as we can tell. And at that point, the universe will have expanded so much that we won't really actually be able to see very many stars in the sky. The galaxies will all be beyond our horizon, and a lot of the stars in our own galaxy will have died by then. And so it's very likely that the hydrogen and the oxygen that's right now in your stomach will be just floating through empty blackness. So eventually, it's all nothing. However, that's a little bleak. To sort of come up with my main takeaway from this, it's that for every single element that we talked about, whether it's hydrogen or the oxygen in a star, almost all of its life is spent sitting around, right? So the hydrogen was made at the Big Bang, and then it spent several hundred million years, a few billion even, before it got into a star and became something better than hydrogen. And then the stuff that's better than hydrogen also had to sit around for billions of years before it got to do anything cool, like become a planet. And then that planet had to sit around for several hundred billion years before it got life. And then we are life. And so what I find uplifting about this story is that you are one of the most interesting things that the universe gets to do. The atoms in your body are mostly going to be sitting around for most of their existence and not really doing anything. But right now, they get to partake in this amazing experience of like experiencing consciousness and like eating hamburgers and watching Avengers movies. And so yeah, it's this story that makes me kind of tear up and thankful for existence. And with that, I think I'm done.
Okay, thank you very much for this talk. I was able to see many of your nice and handmade illustrations.
Mm-hmm.
So there are a few questions on the YouTube channel. So I can see one from Michael Smith. Why do white dwarfs float?
Why do they float?
Explode. Sorry.
Oh, explode. Oh. So it has to do with the so the atoms that are at the core of a white dwarf are under an intense amount of pressure, and the pressure is being sustained entirely by the electrons pushing outwards. And when a white dwarf gets even and the amount that the electrons are pushing back is proportional to how much is pushing down on them. And so when a white dwarf grabs a bunch of material from its nearby companion, the amount that the inner material pushes back becomes so much from this excess mass that's been piling on that the whole thing just explodes.
Okay. Now I see. Yeah, I think there might be a little delay with the people. So now people are saying clap, clap, applause. Thank you. Let me see. I can find another question. Were Venus and Mercury also at one point in the habitable distance from the sun?
Only for the very early stages of the sun's life, but they wouldn't have been in that region for long enough for life to have started on them, we think. we're pretty sure that life never existed on Mercury, just because it doesn't have enough stuff for life to exist there. And life might have existed on Venus, but it would have been a very short window in which it was possible for things to evolve.
Thank you. So if you have a follow-up question, remember you can also write it on the YouTube channel. Then there is, I think, a follow-up question sort of related to the previous one, which says, how long would Mars be in the habitable zone?
For a few 100 million years. So that's during the sun's red giant phase. Okay. And that will only happen. That will only be happening for a few 100 million, as opposed to several billion for Earth.
Okay. I also see in the chat there is a Deich at Deich answering most of the questions. So.
That person is related to me.
Okay. Okay. Then there's another question that just came up, which is, under what circumstances would Earth fall into the sun as it collapses? Intuitively, if the sun loses its gravitational pull, I feel Earth would float away.
Yeah, that's a good question. So this has more to do with interaction between the Earth and gases that the sun is expelling than it does between the Earth and the mass of the sun itself. So as the sun is throwing things away, the Earth is slowly going to lose angular momentum, and it's that loss of angular momentum that'll really cause it to fall into the sun.
Okay. Okay, more people saying thanks. Let's see if another one appears. In the meantime, let me ask something related to what you mentioned at the end, Alex. Mm-hmm. And is, okay, so based on what you were mentioning, now I'm not sure if we are here because a rare like consequence of things that happen, because it might seem, we might also think that generically that stars are born, then they die, they might collapse in certain ways. So based on your explorations in this topic, do you think it's very likely to find life, whatever life might be, somewhere else?
Yeah, I do. So if we go back to the slide where I had all of those if we go back to this slide that has the most important elements for us to exist, mm-hmm. What do you see but hydrogen, carbon, and oxygen? And those are some of those are relatively light elements that can be made relatively easily. And so it's very likely that other places in the universe and even the galaxy have exactly this makeup. And so it would be like sort of creepy and weird if there wasn't any other life in the universe.
Okay, thank you. Then there's another question now from Deich. Why did the inner rocky planets lose their water?
Yeah, it's entirely because they're too close to the sun. And if they don't have an atmosphere, then the side that's closest to the sun is constantly getting blasted with solar radiation. And that solar radiation is going to evaporate and break apart the water into its constituent atoms. Okay,
and then there's just another question just appeared, which is related to that one. If most water on Earth did indeed come from a comet or asteroid, would other planets have been just as likely to have received this celestial dose of water too?
Yeah, that's a really good point. So yeah, it is thought that the Earth and Venus and Mercury and Mars, for that matter, we're all getting basically the same amounts of asteroids impacting them in the early solar system. And so, for instance, we know that Mars has a lot of water. Like it has really big ice caps. And it's likely that that Mercury and Venus did as well, but their water would have been sort of destroyed by the sun.
Okay, thank you. I don't see more questions. People are thanking you, and Astronomy on Tap for hosting this event and programs. Okay, let me just double check. There are no more questions. Good. So thank you, Alex, and thank you, everyone, for participating in this event. Stay tuned on the Astronomy on Tap webpage or also on social media for our next topics and events. Thank you very much. I should mention, if you want to